The last concept for multi-slit diffraction involves the use of diffraction gratings. You have a small section in your text that talks about this. And this would have been something we would have played around with a lot in the lab. They're pretty fun to have. We have this tool in the lab, which is multiple diffraction gratings. Okay, so these little windows, we would shine a laser into those windows and you'd see some interesting patterns that appear on the wall. And what diffraction gratings are, they're tools used by scientists to disperse white light into a spectrum of frequencies. So if I had white light, a white light source where I force the light to be coherent, they're all in phase, and when they hit a diffraction grating, the light would form a white dot in the middle, in the central maximum, and then we would see rainbows appear on the side. We've seen other instruments like glass that does that through refraction, but diffraction can also make rainbows. I want you to stop for a second, press pause, and I want you to think, why would light disperse into a rainbow using the diffraction formula d sine theta equals n lambda? Why would rainbows appear when white light hits the diffraction grating? The other thing that diffraction gratings are used for are to measure the wavelength of light produced by a light source, such as a laser or flames. If I look at different types of flames and the temperature, I can see which wavelengths of light are produced. Something you do in chemistry and physics very soon is if you heat up elements, they start to glow different colors. We can see which wavelengths of light they produced using diffraction gratings. And when we look at stars and other different light sources, we would be able to see what specific wavelengths are produced using diffraction. Here is an example of that. If I have a certain light source, like a xenon light source, and I shine it through a diffraction grating, we get these patterns. You get your central maximum, which looks exactly like the light that comes out of the bulb. But then beside it, that light is split up into the individual frequencies that make it. Okay, so we see these little rainbows. This rainbow over here would be my first maxima, and then this would be my second maxima. You can see they start to spread out, the colors start to spread out, and I can see which individual colors make up that color. So that's my first maxima, second maxima, that's my angle of diffraction. That would be my diffraction grating. But with all this, we didn't talk about what a grating is. Well, a grating is like a piece of plastic. So if I draw a window, and we use machines to cut little slits in it, okay, like we did for multi-slit diffraction. But these slits, you'd have like thousands of them, and the slits would be all evenly spaced. Let's say this is all just magnified. But I would have, for example, very evenly spaced slits that a laser would cut or a machine would cut, and we would have something like 1,000 lines or slits cut in a millimeter. Imagine taking a millimeter and putting 1,000 lines in it. That you couldn't do by your hand. You'd have to make a machine out of it. Well, when we made these types of instruments, we found that they do interesting things with light and really separate them, make rainbows. And they're very useful tools. It's a lot cheaper than making a prism to make a rainbow. And that's where diffraction gratings came from. So with 1,000 lines cut into a millimeter, what would be the thickness of that line? Okay, and the thickness of each line would represent D. D is that thickness of the slit. So what would D be? Okay, so with 1,000 lines in a millimeter, what would D be? Okay, well, let's convert that into meter. If I had 1,000 lines in a millimeter, then that would mean that I would have 1,000 times 1,000, because there's 1,000 millimeters in a meter. So I would have 1,000,000 lines in a meter. Okay, so D is going to be 1 meter divided by 1,000,000, which is going to be 1 times 10 to the minus 6 meters. Okay, so D, the thickness of a single slit in that diffraction grating, okay, the thickness of that slit, D, is going to be 1 times 10 to the minus 6 meters. That's really small. Okay, and that would allow us to really diffract light to a large angle. All right, so 1 times 10 to the minus 6. So you can see that. So whatever the lines are per millimeter, you'd have to convert that into lines per meter. And then if you just invert it, 1 meter divided by the number of lines that would appear would tell you the slit width D. 1 times 10 to the minus 6. Okay, that's important. Why did we do that? Because we need to be able to apply that to the formula D sine theta equals n lambda, where this is constructive interference. That's what occurs with multi-slit diffraction. Okay, so when we look at these diffraction gratings, 100 lines, 300 lines, 600 lines, I'd be able to calculate the thickness of each individual line in that grating by using this relationship. So take a second, stop there, and write that down. This is very important when you're working with diffraction gratings, that you know how to calculate the slit width based on the number of lines per millimeter. It always appears, okay? So once we know how to calculate D, and I know either the wavelength of the laser, I could predict the angle at which each different colored wavelength would appear on my diffraction pattern. And this formula here would explain why the different colors in light have different angles themselves, because they have different wavelengths. Each different wavelength is going to produce a different angle of diffraction. All right, if you rearrange that formula, sine theta is equal to n lambda over d, okay, my wavelength, every different wavelength is going to have a different angle. And that would explain why we see a rainbow pattern appearing when we have a very, very small d, because it really separates those maxima to a larger degree. Okay, so that's the unique part of using diffraction gratings. We can get this rainbow effect. You don't quite see that on a double slit diffraction or single slit diffraction. On multi-slit or diffraction gratings, we get those rainbows. Okay, but not only that, something that we would have done after seeing those rainbows in the classroom, we would have done some diffraction experiments to do two specific things. The first thing we would have done is try to use diffraction gratings to calibrate the wavelength of the laser that we have in the lab. In the lab, we have a green one, but here's a exotic blue laser. And in this experiment, the scientists are shining a blue laser at a diffraction grating and creating this diffraction pattern. They put fog so you can see these lines, and we've shown you that in the class before. And they would project those lines onto a screen. So what you see here on the right-hand side is just kind of a cartoon picture. This would be the diffraction grating. Okay, so that's my diffraction grating. And let's say that this diffraction grating has 300 lines per millimeter. So when I shine this blue laser, so let's just say I have a column of blue light, okay, shining into that diffraction grating, that blue light then forms forms these beams that we see here. Okay, now this beam right here in the middle would be my central max. Okay, and this would be my first order max, and that would also be my first order max. Okay, and then you would have your second order maximum, third order maximum, fourth, fifth, so on. First order maximum, second, third, fourth, fifth. Okay, and this is a classic experiment. Remember, this is multi-slit diffraction, so all these dots are created by constructive interference, and the formula that we always apply is d sine theta equals n lambda. Okay, so how would we use this image projected on the screen, okay, and the 300 lines per millimeter to actually calculate the wavelength of that laser? So first thing I'm just going to do is I'm going to erase these little lines that I'm making over here and show our classic triangle that we would have seen. Okay, that's a triangle that we would have created in many of the videos I've made, and we would have measured that angle of diffraction. That would be the angle of diffraction to the first order maximum. So that's my angle of diffraction to the first order maximum. Okay, so n in this case is equal to 1. All right, so I'd be able to measure the wavelength of that laser by rearranging this equation to d sine theta divided by n is equal to lambda. So we'd be able to solve for the wavelength of the laser. So if we measure that angle, now how do we measure the angle? Well, you can use trigonometry. If I know the distance, if I know the distance between the screen and my diffraction grating, and I measured the distance between the first order maxima and the center of the central maxima, I could then say x over d is equal to tan theta, which at very small angles is also going to be equal to sine theta, or I can just solve for what the angle is and then plug it in here. And then I would plug that all into here, into that equation. And then how do I solve for d? Well, like I showed you above, d is going to be equal to 1 meter divided by 300,000 lines. Okay, so one meter divided by 300,000 lines times sine of that angle, x over d, divided by 1, because that's the first order maxima, would give me the wavelength of this laser. Okay, so I'm not going to calculate it for you, but I'd show you this is the method at which you would apply it in order to calculate the wavelength of the laser. The reason I'm not putting these numbers in here is because this is a lab that you're going to have to do in your first pivot activity. You're actually going to measure these angles and calculate the wavelength of a laser. Or if I told you what the wavelength of the laser is, you can then calculate how many lines there are per millimeter in a diffraction grating. That would be the second experiment you would do. And that's the basic setup on how you apply d sine theta equals n lambda, the diffraction equation, to diffraction gratings. Okay, where the most important thing you need to know is when it tells you how many lines there are per millimeter, you can then use that to calculate the width of each individual spacing by taking 1 meter divided by the number of lines in 1 meter. That's a very important thing to know. Okay, great.